before starting, like, yeah, have you any like anyone coder has some experience in deep learning? Anyone? Yeah, here one or more. Yeah, you. Any? Yeah, that's good. Okay, so I would like to talk about EfficientNet, which is a computer vision set of that algorithm. So there are many there's a common people deep learning and many of the non-members. Like I'll try to explain. So it related to that malaria. Okay, you can take you get the knowledge for that. So little bit about me. Yeah, like vision researcher. I work here at Saama. So I have I code in a hacker and I'm a PyTorch contributor. You know, like TensorFlow, like PyTorch is also a framework. Yeah, I like yeah Linux. Like these are the contents like we are going to see today. This is so far in backbone networks. So so the problem so like what are the advantages behind EfficientNet is like why it is very important. Like, so take the use case like this malaria problem. So while running the model, it should be like very efficient, right? The latency should be very high, and the model should not be very high. For example, if you have a model that is running like capacity, if you have experience in deep learning, you know there's a problem in latency. So for example, like if you have a facial recognition algorithm, it takes a lot of it is easy, but when you employ with deep learning, like it takes a lot of time for inference. Like, currently state of the algorithm as 40 frames per second, right? So you come to know like last week in Saudi, I think so. A man was eating a bun, and the camera detector like he was holding a gun. So there's like it's still a lot of gap in there, but the thing is like it also has latency problem. Frames capturing per second is like bit low in deep learning algorithms, especially in computer vision. So previous before EfficientNet, they use like ResNet, inception, like kind of algorithms. So that the problem with that is like they have the computation is very high. So 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 even Google found out a way to port that like using TensorFlow like to convert that bigger model and to deploy into mobile network. But the problem is like the time goes on and like lot of algorithms came up. It's bit efficient than before and inception network. So talking about that is like so this is the EfficientNet. So like ImageNet, like have you heard of the name ImageNet? Like a few of the film. Okay. So ImageNet ImageNet is a data set like that has 1,000 classes. Like for example, 1,000 classes that includes like classifying flaws, cars, or something like that. Okay. So in that particular data set, this data of the algorithm achieves 84.4% accuracy. Okay, it's still not 90 or 100 because image editor can make millions of images. So still the data part has 84.4% accuracy in the data set. So yeah, that's it. Like and one more advantage in EfficientNet is like it scales like depth channels equally. Uh, so this is one important slide. So you have channels, right? In example, you have RGB channels, RGB, red, green, and blue. So far researchers in backbone networks is that like when you have a in first one in baseline network A, when you have images like when you go down the when you proceed further, the number of channel gets like with is like getting multiplied and the network is getting higher, or they will include higher resolution images. So what it is so when you have three channels, what algorithm does is like three channels get multiplied into 100, 200 channels. So for example, if you take 920 into 920 into 1080p, what is it? It's just like a matrix of numbers, right? So what is that is 920 into 1080p. If you have a image, so every pixel stores some colors. Example, on top, like it have nose, and below it has like kind of stuff, right? So everything is a number. So what happens is like the three channel gets converted into some like 100 channels or 200 channels by the algorithm. I will explain in layman terms. So what 100 channel holds, why it converts 50 channels into 100 channels is that like three channel holds some information. 100 channel stores more information about the three channels. You get it right? Yeah. So like by having like that, like it can able to store more information. That's a key point. If you are really planning, like you have to like, it's kind of like you can able to grasp like yeah, like that's it. So yeah, that's it. Like suppose like he described like he has a algorithm problem. Like he not only had like a 1,000 data set, but also like he didn't give much accuracy. So in that the problem is that like if you in deep learning you should have more images to get good accuracy. So not only with good accuracy, you should also have a good working algorithm to detect or predict whether it has a malaria or not. So that's the thing. Like if you have a malaria in a single channel grayscale images or multiple channels, so those converting into 100 and 200 is like the model can able to capture the three channel into 1,000 channels information. So that's the point. That's the baseline. So what are the differences so far is like with scaling, like with scaling is nothing but like you're scaling three channels into 100 and 200, going with the depth is like so like I have the network, like suppose for example three one input and one hidden and one output. So it's very small in between, like input and output. Instead of having one, I can have more than like 10 or 20. That's the depth. Okay, so that's the deeper. Instead of passing from one to output in between the one hidden layer, I can have more hidden layers so that the channel information gets like learned like efficiently. So these three are the main factors that are like ResNet inception are being used, because they are focused on that right now. They are like kind of using image resolution and network depth and wider network. But the thing here, but the thing in but the thing in EfficientNet is like you can have like even if you're scared of deep learning, if you have a good image resolution, you can have a good accuracy. That's what everyone like takes note of, that you have good accuracy, you can take out that. So what it does in before network is they take good they take 24 into 24 or 296 into 296 something resolution like that, and they get good accuracy. So like the thing is like it's not only relies on accuracy resolution of the image, but also relies on deeper and wider. So EfficientNet like totally scales like these three takes in mind and scales equally. So that's what EfficientNet does. That's what the term efficient comes. I'll explain this compound scaling in the later section. So example is that like, so like this is a one EfficientNet. So my resolution is 224 to 224 into 3 that goes across multiple channels, and like convolution, relu, max pooling, pooling and occurrence of max. Convolution is nothing but like a matrix multiplying into another matrix and getting a number. You just like think of it as a matrix multiplication as convolution operation. Okay. So max pooling is that like in 928 28 images, like I will take first 5 cross 5 grid. Okay. First top of 5 cross grid. So in the 5 cross grid, I take the maximum value out of the 5 cross 5 pixels. That is max pooling. So and fully connected is nothing but, as I said, like between input and output, there's a hidden layer, like something like that, fully connected. So and relu is an activation and softness function. So from single image, the 1,000 values gives the at the last one it gives like one into 100, right? 1,000, right? So the 1,000 are that from one image it gives 1,000. If the model classifies into 1,000 classes. For every image it classifies into 1,000. So at 1,000 you have a probability that which like belongs to that aeroplane or car or something like that. That's a 1,000. Yeah, this is the model architecture. So by going through that convolution, max pooling, and everything, you'll have 138 million parameters. As I said, you should like while moving into deep learning, the model should be like a very small one to be ported into smaller data's, or like whatever the things. Because in deep learning, you definitely need a GPU, but like not everyone has the GPU. It should be like the model should be capable of learning with within a CPU. So that's what the problem with the VGGNet is, like it has 138 parameters. It in normal like this, it has to do 138 million calculations. You think of like that. So it's kind of so another network came like that is bit listen VGNet. So it's also by Google. So the thing here is like in the end, like before slide. So at the 14th and 15th row we have a 10 lakh 27,64544, right? So those are FC, like you can have here FC and you have 10. So but before that the values are much lower, right? Only at this value it's twice of this above value. Can you like literally see, like literally say, like you can see. So like the problem here is like that one layer produces 10 amp parameter, 10 amp calculations when compared to all the above ones. This one layer only FC. So in the above, in the next one, inception network, they got reduced into a smaller one and increased the convolution and max pooling operations. So and you perform on the everything. The calculation is again 138 million parameters got reduced into 6 million parameters. This more the matrix manipulations are very slow. So that's this network solves is that, like, instead of having three FCs which we see in the above one, we have one FC, only one FC. So yeah, here the problem is, like, you can see, I will try to explain lemon. Like you can see in the set 152 you have a connection in between the in between the subsequent, right? So what it does is, like, you have one image and you're feeding the image to the network. So in between the network, suppose in 3x3 convolution, what happens is that, like, so suppose, like, I'm passing one malaria image and trying to classify into some other I'm getting some output as yes or no. In between the information gets lost. Might be, yeah, that's the research here. The information might be get lost. So because in order to solve the problem, so think of like a in the first one, soundcast convolution 64 output is being fed into 3x3 convolution is 64. This means, like, every output you do calculation, I'm going to feed it to another one, so that the model will learn effectively. Okay. So this what EfficientNet ResNet solves the problem. Again, the parameters is 11. It's a bit higher than Inception, but it's very good in classifying. Classifying, it's very good than VJJ and Inception. So the thing here in ResNet is, like, I'm passing one after one after one after one. That but in DenseNet, in above and 2D convolution is being passed to all second 2D convolution, 2D convolution, 2D convolution. Likewise, like second, every output is being fed to another ongoing subsequent layer. You can see the difference, right? Like here we pass one into one. There is no correlation between one and the last one. But here you can see, like, one is being passed into second and third and fourth, and likewise second, third and fourth and fifth, like third and fourth. So this means that, like, this is the same. Like, even if you pause, if I say something here, and if this guy carries information to all the guys, this means that, like, he from one speaking about to the next one, like, if you allow the guy to speak to hello to anyone, this means, like, you can remember everything. That's a, like, basic thing. So the image values gets used by the all layers, like in the sense, like, it carries more information in all the layers. So that's what DenseNet solves. It's like the kind dense is like, it's like the model is dense, right? Every connection is being fed into. That's the name it's called, DenseNet. Yeah, it's you can see, like, it's also very bit low. DenseNet BC. The center one is parameters 1M, 7M, and 27M, 0.8, 15.3, and 15.6. So that they are all the parameters. And the first row you can see, like, 40, 100, 100, 150, 190. So these are the depth which I mentioned earlier. So yeah, a quick summation is, like, VAG has small depth and very high parameters. Inception has getting rid of the FC and used more channel cross correlation. ResNet is like shortcut connections from one to another. DenseNet is like having short connections to all the above layers for each layer. So that's it. Okay. So as I said, like, you just try to explain whatever you know, that's fine. So as I said, like whenever you have input and in between input and output, instead of one, you have multiple layers. As I said, like the information gets flown, and in between input and output and in between the many layers, if you pass one information to all the layers, it actually improves the accuracy. So like, do you think like stacking the layers, like you have like good accuracy? Like, like you have anything about that? Like you're getting the question. Like, are you getting the question? No. Okay. Like as I said, right. When we increase the depth, instead of having one hidden layer in between the input and output, if we have more hidden layers like in between the input and output, you can share more information, right? So, so yes, that's the thing. Like if you have more stacking, like in between the input and output, like if the information flows gradually, like
Or put it this way, like, do you think adding more layers in between will end up in increased accuracy? What's your answer? Because it depends on the parameters that layers extract. Yeah, so it doesn't actually increase the accuracy, right? That was the question.
yeah, it's simple. Like first 2D and last 2D is input and output, for example, and between in between you have intermediate as considered as hidden. So here have in between input and output have three hidden. Okay. Does that mean is like you have like while increasing the depth in between the hidden, can you improve accuracy? That's what my question is. Because the same follows in ResNet. So see, I have added more hidden, right? So like, yeah, you think like even it's wrong, like you can tell me like that's good. Like, you can try to.
So what do you
Adding
think?
layers is it's effective. That's why these ResNet and other layers are using the more layers.
Yeah.
But we have to balance out between with how much layers you can want computational
Yeah.
manage the you are telling latency that also we have to factor in.
Yeah, that's
So we can.
that's also a good answer. Yeah, that's good. So you heard right? Like you use Google, okay Google, right? And you say something in okay Google, like give me something or tell me something. So whatever you say, just remember the long sentence. Am I right? So if you say something very long, it means like you have said like something a very long sentence. I mean, like you're getting right. So the problem here in deep learning is actually the problem arose back in 1990s and problem got solved in 2014. The problem in deep learning is that like if it is a large one, the information does not flow properly. So it's because if you in deep learning you calculate long and then back propagate. Okay, so you use back propagation using a partial derivation. So that thing, the partial backpropagation is done using is done to partial derivatives. So the partial derivatives like just back propagates and updates the error and then goes forward. The thing in backpropagation is that when you have a long sentence, it has to remember. Suppose I had an apple and add juice. So like I had an apple and juice. So it's like it's very small. It can able to remember upon like you can pause like if you have many depth, it can able to remember. But the thing is like you want to like you don't know, right? In deep learning the research is like interpretability is something like you do like a manual like something like that. So interpretability research is very low. You don't know 30% practical and 30% theory and 70% practical. In 70% practical you don't even know what that caused that particular accuracy. You don't even know that many flaw in deep learning. So the thing is like you should remember all the things, right? Sometimes like I had an apple and orange. Sometimes the small bricks I apple add orange. Kind of error, right? So the thing is like it should back propagate effectively, or in the sense like the model, or we can say like the model does not able to remember all the information flows correctly, the sequence. So the thing is like if you add more layer, the more stacking layer, the information gets degraded or it gets saturated. It will not move beyond the particular point. Suppose I add in the first layer I showed you 84.5 accuracies, right? So the thing is like deep learning came out. It was like in 1990s. The research started that like it got very famous in that time, and then due to GPU problems, it got again booming to the 2011. So the problem is that like its computation also like bit heavy, and also like the thing is like even if you have many the answer is like even if you have many stacking one between the input and output, like there occurs a problem, like it won't reach like 84.1%. It won't go above the beyond point. It just starts whatever you train or how many hours you train. It does not go beyond that 84.5 or 80.5 like that. Okay. In small data set, this is 1,000 class image data set, which means you have 1,000 classes, airplane, all that. But you have a binary classification 0 or 1. Suppose like you have to classify this as a char and this as a table. It becomes easy. But when you have millions of images, it becomes very difficult. The model does not learn. It just starts beyond. It does not learn beyond the particular point. So this research is still going on. It came out in 2019, but so far the results have not that kind of like able to solve this problem still now. So the thing is like the same thing. Like even if you add more layers, there after some point it gets degraded. Okay. There are also multiple methods. Like instead of using partial differential, I said like partial differential equation. The other paper can use like, have you heard of in childhood it's like Euler's theorem? Yeah, I kind of try to solve the problem using Euler's theorem. There's a lot of mathematics involved in this. Okay, that's the thing. So okay, I just answered. So that's the thing. I said if you use only network width, that is the number of channels, at some particular point, beyond 80 and 81, it got like it bits like it's not growing, like it gets saturated as the A diagram. And second one is depth diagram. Even if you go start at that point, at particular point gets saturated, and at 82, 81, it got flat one, right? It's not improving after all. Flops is nothing but floating point operations per second, right? Okay, so even if I use higher resolution, it gets slowly sat, and beyond that, R is equal to 2.5. It's not moving beyond that. That's the maximum. So that's one of the problems. So in order to work a model that works better, we should focus on both width, depth, and resolution. We should commonly use. We should effectively use that all the three. So there it comes. This is EfficientNet is like uses effectively. I will try to explain more ways. Okay. So as I said, like have a 24×24×3 pixel, that is red, green, and blue, for example. So this called, as I said, like convolution is nothing but a mathematical matrix multiplication. So here they used something called depthless convolution instead of normal convolution. Normally multiplying, they used depthless convolution. So you have 3 channel images. So 24×24×3, I have 5×5×3, which is nothing but I use, so for every green I have, for every green and red and violet I have the smaller one, smaller 5×5×3. 3 is nothing but total number of 3s, okay, channels. So what I'm doing is like I'm going to scroll everything and try to produce an output 20×20 cross. It scrolls and gives output 20×20×3. Okay. So from 20×20×3, this convolution is called point convolution. Instead of having the middle one like before the 3 different one, I use a single convolution to give only one channel. Okay. Okay. Single channel. Okay. So yeah, like so why is the efficient is like this is the most important one with example. So if you multiply with normal convolution, that is 16 channels, if you have 16 channels and 24×24×3, that moves, as I said, like this 5×5×3 moves around every time, right? Moves around every time. And if you calculate as 4×400 times, its matrix multiplication goes like for 4,42,368 parameters. If you have depthless convolution, like you said before, like 3×10^4 gives 27648, and only one channel, that is 1×1×3, that moves around 4×4 times. That gives so total is 28,416. So as you can see, like normal convolution, normal matrix multiplication, it's having like 44, and here is 28, right? So it's gradual decrease. Yeah, and if you have done matrix multiplication, you know, like if you have 3×3 matrix and you want to get again 3×3 matrix, use again 3×3, you get again 3×3 matrix, right? So you know, right, the basic multiplication, instead of multiplying 3×3 into again 3×3, you can split row into column and give 3×3. Can like you get it, right? Yeah. Suppose like if you are using 3 cross 3 and multiplying with 3 cross 3, you get, so again 3 cross 3 matrix, for example. So this is what you normally do, right, convolution. But also in some cases you can use like instead of multiplying 1 into 3, so it gives the same 3 into 3. Can you get it? 1 into 3 and 3. Yeah. So like the thing is like it reduces the matrix multiplication. So this type of convolution, so the same similar to this depth separable convolution. Okay, it kind of reduces matrix multiplication. So like in EfficientNet they use something called model scaling. So as I said, like depending on depth, there is total number of hidden something like that, and with this like number of channel you are multiplying 3 channels into 100 and 200, and resolution you are going to use 204 or 480. They use some method to effectively make use of both depth, width, and resolution. Okay, alpha is depth value and beta is width value. Resolutions are r power something theta. Okay, something like that. So that when we multiply all the alpha into beta into gamma, that should be approximately equal to 2. You should not go beyond that. But also the other use case is that you should be equal to greater than, it should be greater than 1, all the 3 betas and gammas. So that's what like they effectively used. So they use the grid search, a type of algorithms to identify which parameters are the best. So this is their architecture. So first one is like convolution 3 cross 3 and convolution 1 6, and finally we get convolution 1 cross 1 and pooling and FC. So they at the first time they used 24 to 24 resolution, and after going down the layer, the resolution got reduced to 7 into 7, and the number of channels I said before, right? At first channel it gets 32 channels, 16 channels, 24 channels, 40, 80, and go on. Finally, you have 1280. Layers is nothing but, as I said, in between here, input and output, you have to manage like number of layers. That's like 1 1 2 2 3 3 4 1 1. So it's the same thing. So when you look at this, like the 128, 80, 11, when compared to before, they have 512 channels, 1024 channels. It's very huge. But here it's got like it's very low, 80, 112, 192. So take so here like this is the instead of like what previous done is like if you have 16 channel and you are going to multiply into 64 channels, so that's like 16 channels as more information, 64 channels as more information about the 16 channels. Okay, so this is what previously followed by every architecture, but in that EfficientNet is like 64 channel gets reduced into 16 channels. So take up something as example, like if you have a 16 channels that represents like something like bag or something like that, and again 16 channel gets multiplied into 64 channel, means 64 channels has very minute information, because the channel gets multiplied, you have more information than 64 channels, right? Like 3 channels. So what they did is like instead of going from 16 channels to 64 channels, they reduced 64 channels to 16 channels. So the information flow is that like instead of expanding the 16 channels into 64 channels, which the 64 channels might have information or might not have the sufficient information. So they don't know about that, but they are sure instead of going 16 to 64, you go from 64 to 16. That way 64 channel is like have much information. 16 is a much reduced version. So it can have like a squeezed one, expanded to squeezed one. So that's what like they squeeze and then expand in the final layer. But in the EfficientNet, they expand and finally squeeze. So this is what they have done in EfficientNet. In between, they have depth-wise convolution. Before we see like matrix multiplication, right? So that is depth-wise. Okay, you would like to show? You like to see the code? Like, have you watched Futurama? Code is like as usual, like as I said, right? First I have expand depth-wise, and in between I have a squeeze and excitation module, and again squeeze. So like, have you like heard of the name MobileNet? Yeah, right. There's a one network called MobileNet, which is very famous. It's also by Google. The thing is like it's a very light model. You can with the help of MobileNet, you can do object detection in mobile phone in Android. So it's EfficientNet is very similar to MobileNet. The architecture, the computations are totally equivalent. But the thing is like they just added another one parameter called, they just injected sequence and SE module, and they did a grid search by calculating the width, depth, and coefficient. So apart from that, like I accept that the SE model and grid search, everything is same similar to MobileNet. Okay, the same. I go first expand like PyTorch. This is written PyTorch. So first I expand depth convolution and I calculate SE, and then I project that convolution. So the this is what like in channel, out channel, in is in channel, number of in channel is 3 and mid channel is 6 or something like that. And depth is I do the same thing, the kernel size, and as usual SE module and SE projection convolution. So so like I just named as projection convolution because like if you have like skip connections, like as I showed, right, in between you have like kernel of type of array, right? So one channel produces 16, one module produces 16, another one produces 64 means. So the 16 channels should be equal to 64 channels. Only then you can combine information. So for that, like there's a projection convolution. It just manages every output it comes, like it just equally, like it just takes care of the channel information. So only then you can combine. So same, I pass the input like 3 into 3 into 24, and I get into depth base and I see model and projection convolution. So like, and I have a drop connect, which is a bit like so dropout is nothing but like you have a, if you pass information from input to output, in between have hidden layer. Dropout is like you are telling dropout, you are telling hidden layers to pass one node information, to pass whatever. So that is drop out. You are asking hidden layers to drop one thing or some other thing. So drop connect is instead of dropping the node, you drop the weight, you drop the value itself, the carrying one. So like in deep learning, like weights are the one that carries one information to another, the input to or hidden input to output. So those connections are those sharing one are done by weights. So dropout is nothing but you don't do the calculation, the node one. The weight is nothing but like you just make the weight, the carrying one as 0. Kind of like generalization term. So this is it. Like this is what I've said. So I have the incoming channel. So in here, like here, like the you can see the pointer, right? So 16 to 96. So on 96 to 96, and sequential model you can see like 64 into 4 and the 96 into 24. So this is what like as I said, like it's not like expanding 16 onto a bigger number. This is one block. As I said, right, MB this is so MB 1 into K 3 into 3, like that we have MB con 6 K into 3 into 3, right? So that one MB convolution 1 K into 3 into 3 is this one, like. So this one MB convert to 1 is, this is what happens. Like you're not increasing 16 to 96 or something like that. So from 16, the same here we got the sequential one. We have the final output as 24 channels. So we're kind of not expanding, like just resolution 96 into 24. So actually, like we just change this. you have like any kind of like
What about losses? Since we are reducing from 64 to 16, for example, there will be some kind of loss, right?
yeah.
How are we accommodating for that?
So no, 64 to 16 has good good expressiveness in the information. But when you go from 16 to 16, that's what the problem comes. So, for example, like I have some channel, one channel. I'm going to one channel going into this two channel is expanded into 30 channels. This means that every channel has some square information about that, right? In every channel, we are not sure if you have a line piece here, if this one channel shows information about here and another channel shows information about here, this is not like it does not need, right? Only we need is like separate only in between the middle of the channel we need a line space. So if we expand if it goes from 2 to 30 channels, some channel might not have useful information, but when you have 32, suppose like 30 channels that has like that has information about the face or something like that. So when you squeeze it into 2 or 3 channels, when compared to here, which does not have, some channel might not have might information. Here the thing is like you can say like bit constantly, like it has from 30 channel to 2 channel, like it's bit constant, like these 2 channel are the only one, like it has like more information about this like particular case, something like that.
It might be segmented, right? In some segment, for example, in an image, not all information will be in the center or in one particular area.
Yeah,
it will be in 2-3 areas, right?
Yeah.
In that case, what you are telling is it will ignore other areas and take whatever is necessary, the 2-3 areas or whatever.
Yeah, the authors in EfficientNet, they argue is that like when you go from 30 to 30, so total 20 to 30 doesn't have much expressive power. Expressive power is like the channel having the information value doesn't have much expressive value when compared to 30 to 20.
Mm-hmm.
So that's what, because in ResNet that was one of the state of the art algorithm in 2015.
Mm-hmm.
So that had 2 into 30, but in EfficientNet 2019, it's got like they changed the ideas and turned into 32 to 2. So this what like they have changed. You just this approach increases more accuracy. ResNet I think it had a 77.7 and so this is 84% accuracy. So it's like 7% increase.
Mm-hmm.
So if you have a 7% increase or 3% increase, you can win a medal in CAGR.
Mm-hmm. Yeah. Input sample size will be need the same number of samples as in ResNet or even lower size.
Yeah, they have they have variants like B0, 2, B and something like that. Okay, so B0, 2, B7, B0, B1, B2 up to B7.
Mm-hmm.
So if I'm going to work on 128 into 128 resolution, I can choose B0, or like I need for object direction segmentation, definitely you should not go smaller resolution. You should work with like 640 or 780 resolution. The only then the model length. So depending on 190, like you can choose B6 or B7.
I'm telling number of images, for example. Will it be more or lesser than ResNet?
Yeah, it needs.
It needs more.
Yeah, it needs.
That's the question. That's that.
Yeah. Set my English actually. What would you suggest for binary image classification of images? Which are 4000 to 4000 pixels, 70% of 4000 pixels made as info. Okay. So
You can just ask the question if you're it.
Huh?
You can just ask the question if you're it.
Okay. Yeah. Cool. Hi.
It's Murli.
Hi Murli. Like you said, like 70% of 4000 to 4000 pixel image as info. Like, can you bit elaborate on that point?
If you unmute,
Can
they
we
can talk.
unmute?
They can unmute it.
No, we're not talking. We're not talking.
No, no, unmuted, but they can unmute it. They're asking for it. That on
Probably they have some objects in that particular.
Hi Murli, can I voice out your question?
Hi, can you?
So, if you're asking for which model to use, which refrigerator or something like that.
Yeah.
Basically, maybe the image has a lot of objects and I'm trying to capture them all.
Yeah, I get it. Gopi, it's a 4000 × 4000.
See, anyway, you have to, cut down on the pixel values because no model will take 4000 × 4000. So what happens is, like, we have a lot of intermediate layers, right? So just think of convolving it with tensors of, which has a large parameters, say 10 million, right? So you definitely have to cut down on the input resolution. You can't never, you never could use this 4000 × 4000 as in. So probably you could reduce the image sizes and go with what all the algorithms you have right now. There is one network called EfficientNet, which is high resolution network, which pretty much handles the scenario even if the image is not high resolution. So it implicitly handles resolution issues, as in you give any image of media core images or low resolution images, it pretty much handles the situation well and gives you a good result. So that is for images of less resolution or medium resolutions. Since you have a good quality of images, I would suggest you to go with EfficientNet because it handles depth, width, and what's the other one? Yeah, resolution thing. So I would suggest you to go with the resolution thing, but then do some image transformation, cut down on the resolution. And that's pretty much it. And you have any more questions?
Yeah, hi. Before I shared, they did the grid search on that determining alpha, beta, and gamma values. So the highest resolution they used is I think 900 or 700 into 700 some resolution that is below 1000. But I also doubt that, but it worked in 4000 into 4000. Maybe you can resize it without with aspect ratio, and you can try EfficientNet B7 on that. So B7 is a high computation model. That is a state of algorithm for high resolution images.
Less on parameters as well.
Yeah, less in parameters as well. You have anything like you speak or like you just type like I can answer?
Yeah.
EfficientNet is a commercial implementation.
Yeah,
There's an open source implementation there.
No, that's correct. Commercial products whenever is used in a product. Production normal. Who will use it?
See, okay, so as in a product thing.
Google is efficient.
Yeah.
For the silent translation.
Yeah. So Google themselves uses EfficientNet in their products, like Google Lens and those kind of things. Or if you're asking someone else is using EfficientNet in their product, is that the question?
Yes, that is from the Google one. Right?
Yeah.
Definitely, obviously they will use it.
Yeah.
Like the thing is what you can take Tesla or everything, every model they use their primary role is like computer vision, right? So the thing is they're trying to solve this kind of like a bit touchy and should not be very small. Recently, update came that fuels over 350 million in Tesla 3. Update came last week, day before day. So the thing is like whatever the model comes like it will be used. It's not like a question like who are listening because every side of the algorithm comes they can use.
So yeah, to add to your answer, there is license, right? So like MIT license, Apache license, like you can use it for your research purpose, and still you have to mention, that you have used them, but you can't use it for production version of those things. You can't. It's only usable for research and academic purposes. So like to go and see the license term for which purpose we can use. But I'm sure it is not usable in production thing. They'll show you. Like they're patenting everything, like dropout. Google is patenting dropout, and pretty much other things. There are two patent things Google which filed for patent and have got it. So we can't use it for production and commercial things.
But you can use this. And another thing is like Baidu, right? Baidu search engine. Yeah, China. They were working in several car. Okay, they hosted a competition last month. Think so. Like detecting like at what position the car is moving, like a 3D data. I think like someone used EfficientNet in that, but I'm not sure. To solve the problem, to solve their problem. The winning solution. I mean.
Done? Any more questions? So yeah, we are done. We have some snacking outside. Yeah, okay. For the speakers, yeah.
Usually we have a small from our side for you. And Karan, thank you for explaining such a complex algorithm in a very simple terms. I think I understood it. I hope all the non-deep learning folks also understood it, right? So, yeah, now we can go for pizza.
Thanks very much.